Woohoo! You got it! Or you're close if you haven't got it exactly. Let's walk through it though, just to clarify, because it can be a little tricky. Here's what we want. We want the probability of hair color given a certain eye color. Well, the definition of this conditional probability is just this. The joint of hair color and eye color, the two that we're interested in, over the probability of that eye color, the marginal. So joint over marginal equals conditional. We've seen that before. But we can re-express this joint probability like so. The probability of the hair color times the probability of the eye color given the hair color. So this equals this in the numerator. Our denominator hasn't changed at all. This right here is Bayes' rule. So the marginal of 1 times the probability of E given that marginal over the other marginal is this right here. This step just shows more explicitly how we get the marginal. We take all the joints and we sum over the ones we're not currently interested in. We sum over all the different hair colors to get the eye color we're interested in. So the probability of a certain hair color given an eye color is the probability of that hair color times the probability of the eye color given the hair color over the probability of the eye color. So probability of hair color given the eye color, one more time, is the probability of the hair color, this one here on the left, times the inverse of this conditional. So it's the probability of the eye color conditional on the hair color. Here we're getting the probability of the hair color conditional on the eye color. So that times that over the one that's given, because we're given it. It's out of that. Out of the eye color probabilities, how many of those are hair and eye? Does that make sense? So this right here allows you to go from these three to this one. And boom! Bayes' rule. Very important. It may not look like anything astounding at the moment, but I assure you it's extremely important. So now that we're equipped with Bayes' rule, let's return to our doctor scenario. Remember now, you're a doctor. You know that 1% of the population who comes into your office has cancer. You know that your test results in 80% of people who have cancer actually testing positive. So given that they have cancer, 80% test positive, and 7% of people who do not have cancer will also test positive. So given that they do not have cancer, the probability of testing positive is 7%. So you screen a patient who tests positive for cancer. What is the probability that they actually have cancer? Exact same question I posed to you in the beginning. Now though, instead of just going on your intuition, let's try to apply Bayes' rule to this question. In answering this question, it will be helpful to identify what pieces of information we have and what pieces we need. So we're interested in the probability of cancer given that the test was positive. So if we think of two variables, cancer or no cancer, and positive or negative test, we get a 2x2 table like this. And this sort of probability table should be familiar to you by now. Here's the information we have up here summarized in this box. 1% of people actually have cancer. So what's the marginal for having cancer? Out of the whole population, what will go here? 1%. One will actually have cancer. But if 1% of people have cancer, what percent of people have no cancer? We know they have to add up to 100%, so 1% plus 99% equals 100%. So we have this. 80% of people who have cancer will test positive. So take a minute and try to fill this table out on your own. Then we'll walk through a full explanation. So these are given to us. The probability of having cancer is given. That's 1% of people have cancer. So that's the marginal. The people who have cancer and test positive, the people who have cancer and test negative, you add up all those and you get the total percentage of people who actually have cancer. In this case, that's 1%, so that goes here. So the percentage of people who have cancer added to the percentage of people who do not have cancer, that has to equal 1%, right? 100%, right? So 1% plus 99% equals 100%. So that's 0.01 and 0.99. We're also given the probability of testing positive given that a person has cancer. So 80% of people who have cancer will test positive. But that's not what goes here. This is the joint probability of testing positive and having cancer. Remember, to get the joint, you take the probability of this conditional on this times the marginal. So marginal times conditional gives you the joint. So we're given this, we're given this. We multiply the probability of having cancer times the probability of testing positive given that you have cancer. So 1% times 80% to get this right here. And so that's 0.8%, very small. What else do we know? We know that the probability of testing positive, given that someone has we know that the probability of testing positive and having cancer, plus the probability of testing positive and not having cancer, has to add up to 1%. Oh, no we don't.